All right, so for this topic, I'm going to be explaining the delta epsilon definition of the limit from calculus. So this gives people a lot of trouble because it seems very abstract, but all we're doing is talking about no matter what range you give me for a function to be around its limit, I can always constrict the values I'm plugging in such that they will hit in that range. So let me show you what that looks like. If you've got some limit as x approaches some number a of some function, and you say that that's equal to L, let's say you start with this, which you can come up with however you like, intuitively or otherwise, but let's say you now want to prove that that is indeed the limit. Well, the formal definition looks like this. You say that, okay, if for the difference between x and the value it's approaching, it's always less than some delta, if when this is true, it's implied that the difference between the function and its limit is less than some number epsilon, then we say that that is indeed the limit. Now, this is the thing you have to prove. What's tricky is that you're going to start off over here and work with this in order to figure out what value of delta you should be picking. So it's like, you give me an epsilon, I think about it for a minute, and then I come up with a strategy that for any number epsilon you give me, I'll set delta equal to that, and then I'll always be able to satisfy this conditional statement right here. So this is all very abstract. Let's look at an actual example with numbers and see how this is going to work. So let's say we have the limit as x approaches 3 of 7x minus 2, and we say that that's equal to 19. And now we want to prove it. Well, first I'll look at this just to come up with some sort of idea of delta. So if I look at what this is, this says if I take the absolute value of my function, where my function here is the 7x minus 2, I subtract the limit, so minus 19, and notice we are doing the absolute value of this because what we care about is the distance between the function and the limit, either negatively or positively. And if I say that's less than some number epsilon, where that's just any number you give me, so just call it epsilon, I should make sure this is less than that. Let's see what happens here. Well, I've got the absolute value of 7x minus 2 minus 19 comes out to be minus 21. Absolute value's got to be less than epsilon. I'll go over here. Well, notice now inside this absolute value, I've got 7x minus 21. I can factor that 7 out of there. So I've got 7 x minus 3 needs to be less than epsilon. Well, absolute value of 7 is still just 7. So I can take that outside of the absolute value bars. I have 7 absolute value of x minus 3 less than epsilon. Now I can divide both sides by 7. So I have the absolute value of x minus 3 needs to be less than epsilon over 7. Okay, we haven't done any proof yet. We haven't started using this conditional. What we're doing is figuring out what I should let delta be. Because if you look at this, notice that we have x minus 3. So if you look at your formal definition, that's x minus the value it's approaching. I've got that inside absolute value bars. It needs to be less than delta. I need to pick some number delta, make sure this is less than that, and if from here I can get over here, I've shown that the limit exists and that it is the value you said it was. Well, what if I just let delta equal epsilon over 7? Let's see what happens. So that's some background work. Now we're actually going to do the proof. So let me sequester this off so we can see how this works. So proof. We want the absolute value of x minus 3 to be less than delta. That's what we start with. That's our premise. It also just needs to not be 0. You don't need to worry about that too much. So we just need, this needs to be less than delta and not 0. Okay, well now let delta be epsilon over 7. So whatever number you gave me, I'm going to divide it by 7 and plug that in for my value here. So I'll have x minus 3 is less than epsilon over 7. Okay, let's see what we can do now. We're trying to show that if I start with this right here and I pick some value for delta, that I can wind up over here. I can derive the function minus the limit is less than just epsilon. Well, I could multiply both sides of the inequality by 7. If I do that, I get 7 times the absolute value of x minus 3 is less than epsilon. I'm going to be a little bit rigorous because it is a proof after all. So I can say that 7 is equal to the absolute value of 7. Put that right there. Okay, well if I've got the product of two absolute values, I can multiply their insides. So this becomes the absolute value of 7 and x minus 3 multiplied together. And that's less than epsilon, not 3. Okay, well I can distribute the 7 in, and so I get 7x minus 21. The absolute value of all this needs to be less than epsilon. And now check this out. 7x minus 21, well, let's say I just want 7x minus 2. So I have absolute value of 7x minus 2. Well, what I have here is minus 21. I can write that as this minus 2 and then minus 19. Less than epsilon. Look at what's going on here. We have our function, f of x, 7x minus 2, subtract the limiting value, 19. The absolute value of that, what's that less than? Epsilon. Therefore, the limit as x approaches 3 of 7x minus 2 is indeed equal to 19. Proof complete. So just to recap, what's tricky about this is that in order to figure out what your delta is, you don't actually start the proof right away. You manipulate what you're trying to get to. You try to get some idea of where you're going, what you're trying to come up with. And so you work with this to give you an idea for what you should let delta equal. I let delta equal this, go over here, do some algebra, manipulate, move things around, and you should be able to basically massage your premise and come up with the conclusion. And once you've done that, you've proven that this limit is what you say it is. And that is an example of the epsilon delta definition of the limit.